Okay, welcome back. So the first set of techniques we look at fall into the category of collaborative filtering. So we want to be able to make recommendations of items to users. For example, we have a system like an online bookstore, and we want to be able to recommend books to a specific user. That's the first case. So you want to recommend an item. Item can be anything. It can be a book, can be a video, an image, a song. Well, it doesn't really matter. You'll see the technique is the same for all of them. You might also be interested in exactly the opposite question. So you have a new item coming in, a new movie is uploaded, or a new song, or a new book. And then you want to find out which of my users should I recommend this to, so that it has a high chance of being watched or being bought. And finally, we have this collaborative aspect. So we want to find similar items for a user based on interests of other users. So we look at users with similar interests and look at some items that the first user has, but the second does not, and the other way around, and then we can recommend these items to each other. So that's the technique you have behind systems that give you recommendations like the one shown here. You buy something or you watch something, and then you get this recommendation. Customers who bought this item also bought these other items. So this is not a generic recommendation. This is not the top 5 most popular or most bought books. This is specifically based on what I bought and then what somebody else who might have similar interests bought, but that I didn't buy yet. So that's why I get these recommendations. So what's behind collaborative filtering is that we have items. In this case here, it's not movies, it's fruit. So we have all kinds of fruit and we have all our users. And then remember, the users and the items interact with each other in some way. Interaction can be anything, watching a video, listening to a song, liking something, buying something. For now, it doesn't really matter. So that's an interaction. And then we run this through some techniques, and we can do various recommendations based on this. For example, you can find out which items are related to other items. So a user who liked apples also likes bananas, based on similar interactions here. And you can also find a user item affinity. So for a user, which are the most liked, interacted with items. So the first step that's happening is some kind of data collection. Again, if you have an online website, social website, e-commerce website, it will log all the transactions that you do. Everything that you buy, that you watch, that you interact with, that you click on, that you like, that you forward, anything is an interaction, and it records it in some log file. What we are now interested in here is, once we have all this data, how can we use it to make a recommendation? And for this, we have to go back to undergrad math. We have to work with vectors. So you all had fun with vectors at one point. What's a vector? So a vector is an element in a so-called vector space. Vector space is formed over some set, for example, the set of all the real numbers. So we can have a set of numbers, n dimensions in the space, and these together form a vector. You should also remember that you can visualize vectors. For example, if you have just 2 dimensions, it's easy to draw. You have a space with an x and a y dimension. And then for a concrete value of x and y, you can draw the vector in this 2-dimensional vector space. You can also draw it in 3 dimensions, but then for more than 3 dimensions, it's not really possible to visualize it directly. But the math doesn't really care that you can't visualize it. Very often we look at examples in 2 or 3 dimensions just to understand how it works. But all the calculations are then done with a lot more dimensions. So now what's the connection between these vectors that you all did in math in high school and again undergraduate math and what we do here with recommender systems? Well, what's new is so far you did vectors with numbers, right? Vectors of real numbers, of integers. Here what we do is vectors of items, of things like products or users or documents. So what we do is we represent an item, for example, a movie, as a multi-dimensional value in a vector space. And then once we have represented every item as a vector, we can do something. For example, look at how similar 2 items are. So the idea, the concept of representing items in form of vectors, that's what's called a vector space model. And yeah, we have to do 2 things. First, we have to figure out how to transform our item into a vector space representation. And then second, how can we use it for various tasks like making recommendations? So as another example, again, limited to 3 dimensions because it's harder to visualize anything more, we're going to represent movies as vectors. And we have 3 dimensions, so a vector space of 3 dimensions, where 1 dimension is how many aliens there are in the movie. Second dimension, how many cartoon characters there are in the movie. And the third dimension here, how much the movie is about basketball. So now you can place every movie in this 3-dimensional vector space. For example, if we take the movie The Godfather, it has no aliens, no cartoons, nothing about basketball. So it's going to sit at 0, 0, 0 in the vector space. If you look at the movie Aliens, it has a lot of aliens. So it's going to sit very high on the alien dimension. But it has no cartoons, so it's going to be at 0 on the cartoon scale, and no basketball. So going to be 0 in the basketball dimension. On the other way, if you look at The Little Mermaid, there are no aliens in there. Well, assuming mermaids are not aliens, but there are lots of cartoons, and again, no basketball. So it sits high on the cartoon dimension, but low on the basketball and alien dimension. And then we can take the movie Space Jam. Space Jam has aliens, cartoons, and basketball. So it's going to sit very high in all 3 dimensions. So that's the core idea. Now we take our items, movies, books, videos, music, whatever you want, and you represent them in an n-dimensional vector space. And again, in practice, we have a lot more than 2 or 3 dimensions. But to understand the concept and visualize it, we can look at examples like this one to get the basic idea. So what we want to do is first represent an item as a vector. And then you'll see we have to do various operations on vectors. And one of the first ones is normalizing the length of a vector. Let's look at the worksheet for this week. So here's our worksheet on recommender systems. And what we do is similar to the example I just showed you. We have a number of movies, movie 1, 2, 3. And instead of 3 dimensions, we have 6 dimensions for each movie. Here, I assume we are counting how often a movie has been tagged with that category, but you could also have other interactions with the movie. So you can see each movie has a number of tags, and this is our vector space representation. Yeah, so the first movie, first each movie is represented as a vector in a 6-dimensional space where the dimensions are action, comedy, sci-fi, and so on. So the first movie is going to have the dimension that's shown here. And just to get you started, the first task is to compute the length of each vector, which you can do with the formula that I just showed you on the slides. Now, this is basic vector space math, computing the square of each entry, summing them up, and computing the square root. And then you have the length for each vector here. The second step is to normalize the length. So you can see that a movie is going to have a different length, which basically depends on how often something was tagged. So in task number 2, you have to normalize the vectors so that they all have the same length. And this is simply done by dividing each element by the length of the vector, and then you have a length normalized vector. And this is something we typically do in all the applications we see later. You could have movies that have lots of tags or lots of interactions, and then these vectors end up with a very different length. But after normalizing them, we get 2 vectors with the same order of magnitude, and this helps us make better recommendations and better comparison. So, like every week, work out these 2 tasks, post them on the Moodle forum, and then I'll see you in the next part.